It's early morning on February 15th, 2013. A meteor weighing 10,000 metric tons is about to explode nearly 23 kilometers above Chelyabinsk. Shortly after local sunrise, a blinding sight for the stunned spectators on the ground. A massive explosion equivalent to 440 kilotons of TNT. Hundreds of tons of debris released and quickly moved up into the atmosphere. The highly sensitive OMS instrument on board the Sumy NPP satellite made its first observation of the plume nearly 3.5 hours later, an entire 1,100 kilometers east of the explosion and already at 40 kilometers altitude, well into the Earth's stratosphere. A surprising observation, since the stratosphere usually acts as a bumper that caps aerosols trying to rise up from the lower atmosphere. By inserting a column of data from the first plume observation into 2 NASA models, scientists were able to project the plume's trajectory. The model showed that the plume at higher altitudes, shown in red, would move ahead of the lower layer, shown in yellow. The reason would be the difference in wind velocity at the lower and higher altitudes. Also illustrated here is how accurately the satellite observations coincided with the projected path of the plume. When OMS made its second observation, back at Chelyabinsk, nearly 5 hours after the bolide, there was still evidence of the plume at a lower 30-kilometer altitude. On February 16th, one day after the bolide, the OMS instrument detected the far end of the plume even further at 1,700 to 4,300 kilometers eastward from the explosion. By February 19th, 4 days after the explosion, the satellite observation showed that the meteor debris had circumnavigated the entire globe and returned to Chelyabinsk, forming a complete global belt. The clean shape of the belt was another surprising prediction, considering that northern hemisphere winds during the winter are usually rather inconsistent in direction. A further look into the model simulation showed that evidence of the plume would persist for a long time, which also coincided with the satellite observations. We have now seen how accurately the models were able to project the plume's trajectory. This is critical, since the same models are used to study climate and ozone depletion. The unprecedented sensitivity of the OMS instrument and its ability to see vertical profile of the atmosphere helped scientists track and study the meteor plume for months, revealing a much better picture of what the aftermath on the atmosphere could be from potential future and even bigger events.